We have a I-beam, but this is I-beam for shear stress rather than I-beam for bending stress. But in the exam, you will need to know, both bending and shear stress, because beam carries both stress, right? Shear and bending. So we have I-beam. So let's read the question first. This is a steel wide flange beam. So this is a flange. This is a web. The dimensions are shown here. And we have a shear force, V is equal to 80 kilonewton. In this case, V is given, but another case you can expect, a more general case you can expect is if, for example, if this is a simple beam like that, you can calculate the shear stress from the shear force from the shear force diagram, right? So there are different ways to ask. And it says plot the shear stress distribution acting over the beam cross section. We haven't solved this problem yet, but where are we going to have a largest shear stress? I will give you choices: top, middle, and bottom. A, B, C. Where are we going to have a largest shear stress? Eric says a B, B, B. One more. B, since y is equal to 0. So you are correct. We're going to have a largest shear stress at B, which is at the neutral axis. And the reason is, as Jacob says, when we have a neutral axis, which is y is equal to 0, then the bending stress is a 0. So this is where your tau shear stress is a maximum, okay? Another thing you can find is this is not a rectangular cross-section, but this is I-beam, I cross-section, but still we have a maximum shear stress at the middle. I will give you another example. We have a T-beam like that. And let's say that this is 10 centimeter. Then where are we going to have a maximum shear stress? What if the NA is not, so y is equal to 0? Okay, then Jacob, okay, the definition of y is equal to 0 is, in fact, that your question is related to the problem that I'm just giving you now. When you say y is equal to 0, that means that is the definition of a neutral axis. So your question asking NA is not at y is equal to 0 doesn't make sense. You see what I'm saying? Y is the distance from the neutral axis, right? So you see the point here? So now I'm giving you the asymmetrical. no, in y direction, right? So this case, the middle point is a 5 centimeter, but 5 centimeter is not where you're going to have a maximum tau. So you can calculate the y bar or neutral axis the same way that you learned in bending chapter 6. So then you can determine the neutral axis location, right? Then y is starting from neutral axis to wherever you want to go, right? So then go to the top or go to the bottom. But your asymmetrical cross-section like T-beam, your maximum tau is still at the neutral axis. That's what I'm trying to say. Okay. And what will be the stress at the top and bottom? Shear stress at the top and bottom? 0. That's correct. Okay, so these are the things that you can know before you solve the problem, before you calculate. And let's check that if this assumption is correct. Not assumption, but our guess is correct, okay? Again, I will start with the shear formula, VQIT. And V is 80 kilonewton. And I. We need to calculate I, right? So this is a 300. This is 20, 200, 20. And this is symmetrical, so I know that our neutral axis is at the middle. This is a neutral axis. So then in this case, you don't have to really determine the neutral axis location. You can actually get it using the symmetry. And there are different ways to calculate I, but in this case, I'm going to have a 2 area like that. So we have a big rectangle, subtract this rectangle using BH cube over 12 formula. So big rectangle is what? 300. H is 220. Cube over 12 minus small rectangle, the 2. So width will be 280, right? Oh, by the way, I didn't give you the dimension for the web thickness. Oh, So this is a 15 millimeters, so I actually got a wrong B. So 15, which means that 285, right? And height is 200 cube over 12. So everyone follows what I'm doing, right? Nicholas asked that H is 240 for the big one, which is correct. Very good. It should be 240 because we have a 20 up here, 20 up down here, right? Thank you, Nicholas. So then you will get 155.6 10 to the minus 6 meter force power. Okay, so we just calculate I, and we need T and Q, right? So here's something that I want to tell you about T for I-beam. For the rectangular, T is the width of the beam, which is a constant, right? But for the I-beam, how many T's we have? 2, is that right? We have flange T, which is 300 millimeter in the flange, and 15 millimeter in the web. So interestingly, back to the equation here, since T is 2, so that means we will have a discontinuity of the shear stress distribution in the flange and in the web. And can you guess where we're going to have a larger shear stress? Is it in the flange or is it in the web? In the web. The reason is very obvious, right? Because if we have a smaller T, which is in the web, we're gonna have a larger T. And also we know that tau at A, which is away from the neutral axis, if we have away from the neutral axis, tau becomes smaller, right? So we're gonna have a lot larger stress in the web, which means we put the flange away from the neutral axis to carry the bending moment, right? Because we have a larger I. So that flange is used to carry the bending stress. And we know that bending stress is larger away from the when we have away from the neutral axis, right? And web is to carry the shear stress. So you can see that This I-beam is very well designed, effectively carry the both bending stress and shear stress. So this is a very clever design to carry both bending and shear. Bending is carried by flange, shear is carried by the web. Very cleverly done. That's why you see a lot of, I-beam as a structural member for the beam. You know what is the opposite design of this, the I-beam? Can you imagine that? This kind of design. This is, cross section, right? This is very poorly designed in terms of, structural member for the beam. And this is the opposite way to design to the I-beam. That's why you don't see, this kind of cross section in construction site. Okay. So far so good. And the only thing left is a Q, right? We need to calculate Q. So for Q, we need to calculate for two parts. So then one that we have, I'm going to use a black here. And one that we have at the web. We have two different area. So and what we're gonna do is we are going to have we want to calculate the Q at this point, and this point, right? To be more precise, okay, let's do it this way. To be more precise, so we have this web, and we have one is right above this, the flange line, flange and web interface. Second is right below that interface, okay? And then I'm going to call this 1, 2, 3, 4, okay? What is Q1? We will start from the Q1, from the top. Without calculating this, you already know the answer. What is a Q1? 0. That's correct. Because Q is area times the distance, right? But area is at the top is 0. Very simple. Q2. What is the A prime for Q2? Or to be consistent, I want to have A prime, Y bar prime. So Q2 includes the flange, right? So the area is 0.3 and 0.02. This is flange. And then distance from the neutral axis to the center of the flange, which is 0.11, 0.11, right? Everyone can follow me, right? So then this will be 0.660 times 10 to the minus 3 meter square, not fourth power or meter cube, right? Not meter fourth power or square. And Q3, Q2 and Q3 will be the same, right? 0.11. So in this case, we use the flange. So this is from the Y bar prime and Y bar prime. So then we have Y bar prime is the center of the flange. So then we have 0.1 meter at the bottom of the flange plus center, which is half of this. George, does it make sense? Okay, good. And Q3 is the same as Q2, but I put it this way because Q2 and Q3 will be the same, but your T will be different, right? At these 2 points. So then I intentionally include that. The rest is Q4. And Q4 is supposed to be maximum. And in this case, we have a 2 area, right? So then we need to have a summation. So then area of the flange, which is 0.3 times 0.02 times 0.11, which is the same as Q2, right? And then we have web. area of this web is, width is 0.015, height is 0.1, and then half of this, which is 0.05. So I can say this is flange, this is web. Of course, this is a flange. Is equal to 0.735 10 to the minus 3 meter cube. Any questions so far? If not, then we are now ready to solve the Q. Awesome, Anna. Then again, I'm actually putting back to this points. So then we have 1, 2, 3, and 4. So what we're gonna do is we're gonna have tau at 1. Tau at 1 is 0 because Q is 0. Tau 2 is VQ2 IT2. So V was 80 kilonewton. Q2 was 0.66 10 to the 3 minus 3. I was 1.55.6, 155.6, 155.6 10 to the minus 6. And T2, what is the T2 here? 0.3, correct? It is not what is that? 0.015, okay? So then this is 0.0. Then you will get 1.13 megapascal. Tau 3, just below the flange, okay? VQ3 IT3. Since B3, Q2 and Q3 are the same, so then numerator is the same. I is the same. And T3 is different. What is the T3? Awesome. 0.015, correct. Then you will get 22.6 megapascal. So if you see these 2 points, 2 and 3, and comparing this tau, you see that there is a big jump, right? So in the web, we have a lot of shear stress. So when you design a I-beam, and when you select the the material for the web, or determine the width of the web, you need to be careful for the shear. Okay, and flanges have exposed to the very small amount of shear force, shear stress. Okay. Finally, tau 4. So we have these 4 shear stresses. And before we solve this problem, we knew that tau 1, which is at the top, is a 0, and the maximum tau is at the center, which is a 4. And you can see that there is a, our guess was right. So what you're seeing here is using this tau at different locations. I do a shear stress distribution from the side. So you can see that our maximum tau is here at the neutral axis. And right above the web, we have a 1.13, and then we have big jump to the 22.6. And these shear distribution is a quadratic, so then this is a curved, and then this is also curved. So distribution, shear stress distribution is something like this. Make sense? Okay, so this is a shear stress distribution for the I-beam. And how does the bending stress distribution look like? So bending stress distribution, and this is neutral axis. So then this is a neutral axis. And anyone can guess how the bending stress distribution look like? What is the bending stress at the neutral axis? Positive at the top and negative at the bottom. So that's correct. So then we have, in this case, we have shear stress and shear force, but we are assuming the positive with the positive moment. Right? Positive moment is this direction, right? So bending stress at the neutral axis is 0, right? Awesome. And we know that we have a maximum bending stress. Yes, this is I-beam. We are solving the same I-beam. So then still, we have a 0 bending stress at the neutral axis. How about top and bottom? We're gonna have a maximum. So top is what? Under the positive moment. Compression, bottom is tension, right? And we're gonna have a maximum bending stress, top and bottom. One thing we want to be careful is what happens at the interface between the flange and web. Shear stress, we have a discontinuity like this. But are we going to have the same discontinuity for the bending? This is a very important question. And in fact, that we solved this problem in chapter 6. What will happen at the interface between the flange and the web? It will have a bump like this. Answer is straight line without a jump. Can anyone guess why this is a straight line? The reason we don't have a jump or bump at the interface is if you look at the formula here. In the shear stress formula, we have a T, right? This jump is due to the beam width is changing from the flange to the web. But if you look at the bending stress formula, there is a no B, no width, beam width. So then this is only the function of y, which is the distance from the neutral axis. This is a straight line. And this is positive, so then this is or I can draw this as negative, and this is positive, right? Tension, compression. Another reason that why this is a straight line is due to those four beam assumption, right? Plane remain plane. This is the deformed plane, right? Due to the bending stresses. So this should not have a jump like that, because if that is the case, then we have a warp of the cross section. So then plane remains, plane assumption is not valid. Okay. Very important.